Hello everyone. We will be starting a set of tutorial, and this is our first tutorial, and we will see how to find the displacement of a cantilever beam for a linear elastic material. So let's say we have a cantilever beam. So while we solve this problem by hand, we idealize it as a one-dimensional line element. Let's say this is subjected to a distributed load W, but actually in real life it's a 3D beam, and the support is fixed like this to one corner. The whole surface is fixed, and this is subjected to a surface load actually instead of a line load. And for this specific problem, let's say our modulus of elasticity is 200 megapascals, and the length of the beam is 2 meters. Of course, this beam in 3 dimension will have a cross section. So why this is important? Since we will solve this problem as a three-dimensional element in Abaqus, we have to specify some dimensions. And this is subjected to uniform pressure of 50 kilonewton over meter squared, or a surface load. So this cross section is, let's say, 300 millimeters by 200 millimeters. So we have to, if we multiply this pressure by the width of the beam, which is 0.2 meters, it will give us the distributed line load along the length of the beam, which is 10 kilonewtons over meter. And the maximum displacement for this beam will be at the tip, which is WL to the 4 divided by 80I. You can find this in any book, or you can derive it using slope deflection or stiffness method, or any other method that you feel comfortable with. So in order to find the displacement, the maximum displacement or deflection in this case, and let's calculate the moment of inertia. This member will be subjected to bending in the strong axis, let's say AA, which is this an axis passes the centroid. And the formula to calculate that for a rectangle is 1 over 12 times width times height to the 3. So this moment of inertia will be 4.5 times 10 to the power 8 millimeter to the 4. So let me multiply it with the modulus of elasticity, which is 20,000 megapascal. It will give me a number 9,000 kilonewton times meter squared. So I calculated this by hand. Why I'm calculating this? Because later we will compare our solution with the analysis of Abaqus. And Abaqus does not have any unit, so we have to specify something. For this problem, for this tutorial, I'm going to use millimeter for length, and for force I'm going to use Newton. And since our pressure is applied as kilonewton over meter squared, I need to change this, and it will be 0.05 Newton over millimeter squared. So let's start. First, you can see there is a module, list of modules like part, property, assembly, step, interaction, load, mesh, optimization, job, visualization, and sketch. So I'm going to start from part. So here I am actually in the part module. I will define all my elements and geometries. So let's say I have a reinforced concrete beam only. I will define 2 parts, one for reinforcement and one for beam. Since here I have only beam, I'm just gonna use one part and I will name it beam. Later in the next tutorials, we will have some different elements and also some complex problems, so we will define them later as well. So here this beam is a 3-dimension, deformable, because it will go undergo deformation. It's a solid extrusion. In the approximate size, we can change this to any number that we want. It is just the viewport of the window. The viewport will be changed in the window of Abaqus, nothing else. So let's make this 400. It doesn't really matter. So here I need to specify the surface, one of the surface of the beam. So let's say I'm gonna create a rectangle. It doesn't matter. As you can see, as I change the mouse, the coordinate of XY direction will change, and this is the center of the Cartesian coordinate system. As you can see, it's 0, 0. So don't worry about the length and width of this rectangle. So if you go here, add dimension, just click on this line. Abaqus will give you the dimension as 45. So as I said before, I'm going to use millimeter for all the length dimensions, and I'm going to use Newton for force. So this is, let's say, the depth of our beam. It was 300 millimeter. I'm just going to put 300 here. I will enter, and as you can see, I can auto fit the view all the time. It is 300, it's changed. And also this is, let's say, the length of the beam. And the length of the beam is 2000 millimeter, which is 2 meters. So I will also change this. Again, I need to set it to the viewport. Now you can see that this is 2 times 10 to the 3, which is 2000 millimeters and 300. So right now I'm done with this. I will just say done. And you can here see that Abaqus is asking me to define the depth, which in my case, this is the width of the beam, which was 200 millimeters. I will say OK. As you can see, a solid extrusion part is created, 3-dimensional. Here we can edit and create some partitions, and I will show you all the functions and features of the other icons on the next tutorials whenever it's required. So right now it's only one part, and we create it. And as you can see here, this icon, Part Manager, if you click, you will see that there is a beam 3D deformable. After part, we will go to the property. Here, this module is basically to define the material, the cross-section, and other things. So for the 3-dimension, we have already defined the cross-section, so we don't need to worry about this. So let me define the material. Create material. This is an elastic material. So we are assuming that this material is linear elastic. For the other tutorials, we will also see for some other properties like elastoplastic and also non-linearities arising from concrete or any other material. So I'm going to go to mechanical, elastic. We are neglecting the self-weight of the beam, otherwise we would go to general and define the density. So right now just mechanical, elastic. As you can see here, the types, there are isotropic and anisotropic materials. So for our case it's isotropic. Abaqus will ask me about the Young modulus and Poisson ratio. So Young modulus is 200. It's 20,000 megapascal, in Newton over millimeter square. Be careful about the units all the time. In Poisson ratio, in my case, it's not important, but Abaqus needs to know about it. So let's say just random value 0.2. You can give 0.3 or 0.15. Nothing will change so much in our problem because we are not interested in the lateral deformations, and there will be no lateral loadings. Okay. So right now my material is created as elastic, and if you go to Material Manager, you can see that there is an elastic material, and if you go to Edit, you can see that there is the modulus of elasticity and Poisson's ratio. Okay, now I will go to create a section. I'm going to create a section, and the section is solid, homogeneous, a 3-dimension. There are some other shell, beam, or something else as well for the cohesive elements and etc. So the material used for this section is of course elastic. This is the only material I have defined so far. I will say OK, and now I will assign this section. So this basically means I'm telling Abaqus that this part is a linear elastic material with elastic modulus of 20,000 megapascals and Poisson ratio of 0.2. When I say OK, the color will change. And after that, I will go to assembly. I will just create instance. I will independent. I'm going to use select this because later we need to mesh it, and we need something to talk about the meshing part as well. I will say OK. And as you can see, this beam is right now assembled. The next operation will be we need to go to define our step. Step is basically the create step tab. Basically, so it's related to the type of loading, for example, or the type of problem. So this problem is a static general. You can also do some heat transfer or mass diffusion in Abaqus. So I'm going to just choose a static general, and I'm going to turn this NI algorithm off, but later for the non-linearities we will turn it on. It will help us to converge to the solution easier, faster, without any error. But right now, since there is no non-linear effect, we will just keep it as off. For the incrementation, maximum number of incrementations, we can just change this to, let's say, 1000 or anything. And the initial, let's say, 0.001, and also the minimum and maximum, we can play that with this. So later on, the importance of this incrementations, we have to talk more, but for this problem, it doesn't really matter. Just keep it as default if you wish. And after the create step, if you go to step manager, this is the step static general that we defined, and also there is an initial step. This is by default from Abaqus. This is from the initial before any loading or any change in temperature or anything happens. This is the original condition of the problem. And now here is create field output. This is basically Abaqus has a default created field output. If we select on the field output manager, we can go to edit. So this is basically what things do I need as an output. So I need the stresses, maybe strains, displacement. In this case, I need the translations and rotations. So this is the only thing important for me, but I will keep it as default as it is. No problem with that. Interaction module is used when two surfaces are somehow interacted with each other, frictionless or having a friction, or let's say something is tied with some other sheet. But in our case, since it's only one part, we don't need to worry about the interaction module now. So we have a lot to talk about this as well. And next one, the loading. In this module, we will define our boundary condition and our loading conditions, or the tractions basically. So as you can see in our problem, we have a fixed support at the left end, and we have a pressure loading. So first, I will just go to this, create boundary condition. I will choose initial because it's even before the application of the load. Mechanical, displacement, rotation. I will name it boundary condition, or you can even name it as fixed support, whatever you wish. And right now, Abaqus is telling me basically to choose a point or a line or a surface to apply this boundary condition on. So I'm going to choose all the surface and say done. Now it's telling me which degrees of freedom you want to be restrained. So for a fixed support, no rotation and no displacement. UR is the rotations and U is are the displacements. U1 is the displacement in the X direction. U2 is the displacement in the Y direction, and U3 is displacement in Z direction, and UR are the rotations in X, Y, and Z directions. So as you can see here, the viewport, I can adjust it as X, Y, Z, so you will understand. So I'm just restraining all of it. And now I will go to create load. So the create loading is in step 1. Mechanical, it is a pressure. So pressure is toward the surface. So our loading is also towards the surface. You can also, there is concentrated force or point loads basically. You can like pipe pressures depending on the type of problems, and surface tractions, body forces, which is the self-weight, gravity, line load, any type. So I'm just going to choose pressure here. Say OK. Abaqus telling me to apply, to select a surface that you want the pressure to be applied. I'm just going to choose this. Say done. Now it's asking me for the magnitude. For our case, the magnitude, we have to be careful about the units. It's 0.05 Newton over millimeter square. I'm just going to say OK. And as you can see, the loading is also created. The next one is the mesh. We have only one part, which is the beam. So if I come here, see part instance for now, it's basically asking me for the dimension of the mesh size. So this is important because Abaqus is solving this problem not in an analytical way, but in a numerical way. So this will be an approximated solution. So as we decrease the size of mesh, we will increase the number of our elements, and we will increase the accuracy of our problem. We will see it now. Like, let's say I'm going to choose 100. So 100, since I'm using the units as millimeter, so my each element, since this is a 3D element, my each element will have 100 millimeters in each cubic direction, like in X, Y, and Z. I will say apply. And now I have to come this to make sure assign element type. I'm going to choose my whole beam. I will say done. So this is a 3D stress, standard, linear, and here you can see that C3, D, 8R. We know that in 3 dimension, any element will have by random and 8 nodes. So I will say OK. Now I will just mesh this part. OK to mesh the part instance. I will say yes. Right now you can see that this beam has been meshed. And now I will go to job. For this, right now I don't need optimization. I will go to job. I will create a job. You can name it anything you want. So let's name it job 1, which was by default. It doesn't matter. And I will say OK. By parallelization, you can increase also the processors and etc. But for this problem, we don't need that. It's a very simple problem, and it will not be very expensive. By expensive, I mean the computational time will not be very long. It will be short. So right now we can go to job manager. If we can go, our job is created and our status is none. We have to submit this and see what happens. So let's submit this job. Say OK. And we can also monitor it, like what's going on. So when this is since we have defined one step, when this total time is 1, it means that the analysis is completed. We can close. Yes, we can see that our status is completed just by clicking the results, or here visualization. But by clicking the results, it will just redirect us to the visualization tab, if you can see. And I can plot contours on the form shape. I can see here. And here are my field outputs. So U is the displacement, U2 is the displacement or deflection in the Y direction. As you can see, the maximum displacement is in the blue part, and it's minus 2.54. So 2.54 downwards. But when we solved it by hand, it was 2.22, not 2.54. This is because of the mesh size. So if we decrease the mesh size, we will get closer to 2.22. So let's do it. Let's decrease it a little bit. Let's go back to mesh. Let's change this, for example, to 50 and see what happens. You will see as I reduce the mesh size, I will get closer to the actual analytical solution for this problem. I will submit it again and wait for it. Yes, it's completed. Let's go and see the results. U2, as you can see here, the maximum is again on the tip displacement, of course, and it's minus 2.33. So before it was 2.54, right now 2.33, which is closer to this. So we can go back once again and even decrease the mesh size more. So the mesh size is very important for large scale problems, because if you use small mesh size, it will take sometimes for analysis hours and hours. So there should be some optimization between the time and the number of elements. So, but for this problem, it really doesn't matter because it's a small problem. So let's decrease even the mesh size from 50 to 25. First, we decrease it from 100 to 50. And now let's run the analysis again. And as you can see, here I increase the number of elements by decreasing the mesh size. The analysis time will increase as well. It's running for now. So first it was 2.54, then it was 2.33, but the actual solution is 2.22. Let's go and check the results right now. So it's right now 2.28 something. So as you can see, we are even getting closer, but I will stop at this point by the number of meshes. So if you decrease it even more, maybe to 1 millimeters, you will get even very closer, like 2.23 or something. Also from this output, I can have like reaction forces, strains, and all the other outputs that I requested for, or stresses. S11 is here in the X direction, or the principal stresses, S22, S23, in the principal directions, like right now X, Y, Z, and the others are the shear stresses. Let me look at the support reaction. RF1 is the reaction force at the X direction, and it's only existing here. In the other parts, it's 0 because we have only support here. And if we go back and see the displacement in the Y direction, the red part is 0, which is closer to the support. So the support will not deform because we have restrained it, not only in the Y direction, but also in the other directions. The displacement of this point should be 0. And it's closer to this color, and between these two, which is even less than 10 to the minus 4 millimeters. And also U3 here is the same. So yes, of course, it will also deform in the other directions, X and Z, because we have specified a Poisson's ratio, but we are only interested in U2. Thank you for watching this video.